Hello and welcome to Homework 2, Part 1. In this part of the homework, we are given a problem in which we have a sealed cylindrical tank. And what we are asked to do is find the rate at which the fluid level drops if we have poked a hole at the bottom of our tank and our fluid starts exiting the bottom of the tank through a very, very small hole. Now, we are given values for capital H, which is the height of the cylindrical tank, and lowercase h, which is the initial height of the fluid. And we're also given like the cross-sectional area for the cylindrical tank. And we're going to plug all of those numerical values in Python in the latter half of this video when we actually calculate the value for the values that they give us. But here first we're going to simply derive an expression to see how the fluid height changes with time. So the first important thing to know here is that we want to visualize this. So if we have a height versus time plot, eventually what's going to happen here is if this hole is very, very small, the fluid height will level out. We will get to a point to where there's no more flow going out of the cylinder. So we'll be going down, 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 and eventually it will level out to some constant fluid level. So what we need to do to solve an expression for how the height changes, or the fluid height changes with time, is to use Bernoulli's equation. Now for Bernoulli's equation, we need to have 2 points in which we either know the pressure or the velocity so that we can solve for an unknown. So what we're going to do here, I'm going to write Bernoulli's equation down here. It is P1 minus P2 over rho plus V2 squared minus V1 squared over 2 plus G times Z2 minus Z1, Z just being the position that we're at in our system. So what we're going to do here is we're going to first set this here, this right at where this hole is, to P2. So that will be our first area that we know. And we know here that the pressure right at the hole here is going to be equal to the outside pressure way outside of the cylindrical tank because it's a sudden expansion going from here to there. So we'll set that as P2. So we have our P2 here right at where this hole is, where the fluid is leaving. And we're also going to set our P1 here in the headspace of this container, headspace being where the air is in this container, so above the fluid level. Now what you'll notice here is that P2, like I said, is equal to the pressure outside of the container due to the sudden expansion, but P1 will be changing obviously when we decrease the fluid level H. So P1 will be dependent upon the volume that's changing and the height that's changing as well. So one thing I forgot to put here is that in the Bernoulli's equation normally we would set this equal to the negative amount of frictional heating that is normally present in this situation. However, we're going to assume here that there is none, so we're just going to set this equal to 0. So now what we need to do is set up an expression to see how our P1 changes with the fluid height level. Well, the first thing that we can note here is that the number of moles present here in our headspace will always be constant, whether we're decreasing the fluid level or increasing. So the number of moles here will be equal to this will be equal to PV over RT. So we can simplify this if we look at the initial situation. So initially we can say that the pressure inside this headspace is 101325 multiplied by the velocity here, or the volume here, excuse me, which will be the cross-sectional area, we'll call that AC, and times the height, which is H, big H minus little h. So big H minus little h. And this will all be over RT. And here we will say that temperature is constant throughout this process, just to keep the calculation simpler. So from here we can get to our P1. So we have P1V equals to nRT, with everything here on the right side being a constant. So simplifying this, we will have P1 is equal to nRT over the volume, which is the cross-sectional area, multiplied by big H minus little h. Now we have to be careful here because this little h is now not, it's not this initial height now. Since we have written our expression here with the constant number of moles, this will be any height now that is changing when that fluid level decreases. So this will be our expression here for P1, and like I said, we also know P2, which is just equal to the pressure that is outside of the container. So now what we want to do is we want to plug our n here that we solved for the number of moles into our P1 expression here. So plugging this in, again, we have to be careful here. I'm going to go ahead and label this as HI because this we said was at the initial situation where we have this initial height here, and this lowercase h down here is the height that changes with time. So plugging in n here, we see that the AC and AC cancel, as well as RT and RT. So what we will be left with is that P1 is equal to 101325, which is P2, multiplied by big H minus the initial height over big H minus little h being the height that changes with time. So now what we want to do is we want to go ahead and plug everything into the Bernoulli's equation here. And what we're going to do is we're going to solve for V2, the velocity of the fluid going out of the container. Now ultimately, like I said, we want to solve for, we want to have a differential equation to see how the height changes with time. But if we get at the V2 here, we will be able to get that, and I'll show you when the time comes here. So I'm going to erase this here. Let me put my P1 up here. So P1 is equal to 101325, H minus HI, H minus little h. So if we want to solve for our V2 here, we'll have V2 squared over 2. And what we're going to do here is we're going to say that the velocity at point 1, so the velocity right here, is going to be negligible. Since this hole here is so very, very small, we essentially will have very, very little velocity here changing at these P1 points. So we're just going to ignore that and say that it is not changing here because we have a big cross section and a very small hole with fluid going out. So solving here for V2, bringing this P1 minus P2 here, I actually think I put this wrong here. So hopefully I'll go back and make a note here in the video, but this is P2 minus P1. So when we bring this over to the other side, it will actually turn into P1 minus P2. So out front here, we will have our G here. And what we want to do here with this Z2 minus Z1 is we want to set our Z2 here at 0, and we want to set our Z1 here, we wanted to set our Z2 here, at 0, and we want to have our Z1 at position here, so our position here will be at the level H. So we actually have a negative GH here, but when we bring that over to the right side, it'll be positive. So we'll have GH, and then we will have, bringing over our P1 minus P2, well, we have 101325 in both of those terms, so we can take that out, 101325, divided by rho, taking that over. And this will be multiplied, since we took out 101325, we will have big H minus HI over big H minus H, and then multiplying 101325 for our P2, we'll just have 1 here. Okay. So solving this further, solving for V2, we will see that V2 is now equal to the square root of 2 times GH plus 101,325 over rho times H minus HI, big H minus H minus 1. This is all under the square root sign here. So this is our V2 here. So let me erase this here just so we have a little more room here. I can't believe I wrote that wrong on Bernoulli's, but I'll make a note in the video where I wrote it down wrong. But we know now that I caught the mistake. So I'm going to rewrite this here up here. So have V2 equals square root 2 times G H plus 101,25 over rho H minus HI H minus H minus 1. Okay, so now we want to get to how the height of the fluid changes with time. Well, what we can say here first is the flow rate going out. So the flow rate going out, so Q out, will be equal to V2 because we're at this position here. So the velocity going out times the cross-sectional area here. So we'll have AC. Okay. All right, so I knew something wasn't right there. It's not the cross-sectional area of the tank here. The flow rate going out will be the cross-sectional area here of the hole, or the area of the hole here. So I'm just going to denote that as the area, so A, hole. And if we think about this logically, the flow rate going out of this tank will be equal to the negative change in the volume. So volume will be decreasing with time. So, or if we want to rewrite that, we'll have d volume, so the change in volume over dt is equal to the negative flow rate going out. Or like I said, it's easier to think of it as the flow rate going out is equal to the negative change in volume with respect to time. So now what we can do here is this change in volume here. We will have a constant cross-sectional area. It will not be changing. However, height will be changing. So we can pull cross-sectional area out. AC, DH will be changing. So AC times the height is obviously the volume, but DH or H will be changing. So we have DH over DT is now equal to negative Q out, which is just negative area of the hole where the fluid is going out times V2. So now that we have V2 here, what we want to do is we want to plug this in here, and we want to solve this as a ordinary differential equation. Now, as you can see, this would be really painful to solve by hand. So we're actually going to go into Python and solve this, and we'll have values here, like I said, for our fluid height, our initial fluid height, the height of the cylinder, the cross-sectional areas, and so forth. So let's go ahead and Python and code this up. So what I've gone ahead and done here is entered in our known values here. So the problem asked us to solve this numerically, so we obviously had to have some given values. So we have things such as, obviously we know G, the gravitational constant, which we will need to use. We have the external pressure, the height of the cup, as well as the initial height of the fluid, and the hole that the fluid is leaving, the area of that, and the cross-sectional area of the cylinder itself. In this T end here, this will be used for plotting purposes at the end when we want to determine how long we want to run the simulation and plot it on a graph. So I'll get to this one at the bottom in a little bit. But what I'm going to do first here is import numerical Python, or NumPy, as NP. This will allow us to use several mathematical commands in order to do the calculations that we want.
So what we first need to do is we need to isolate the right-hand side of our of the change in height with respect to time, that expression that we had derived previously. And what we need to do is supply that right-hand side to Python in order for it to calculate the left-hand side, which is what we want ultimately, which is the fluid level height changing with respect to time. So what I'm going to do is define a function, and I'm just going to call that function RHS for right-hand side. First here will be the independent variable, which in our case is time, and the dependent variable, which is the fluid height, and we will need to have this as a vector. I need to put a colon here, but we'll just be grabbing the first value um, from this vector. It'll only be a vector of one value, so this um, brackets 0 will call the first value in that vector, even though it'll only be a one value vector. So what we need to do here is we need to supply the V2 equation. So V2, if you'll remember, is the square root. So I need to put NP SQRT, which allows us to calculate the square root. I'm also going to take the absolute value because at the end here, we're not going to be wanting to get negative numbers. So the absolute value, and then we will have 2 G times H. And if you remember, this is what we had derived, the expression for the velocity coming out of the hole. We derived this previously. So I'm just entering in the equation here. So G times H plus P ext, so the external pressure, divided by the density, RHO. This was then multiplied by big H minus the initial fluid level, divided by big H, the height of the cup, minus the H that is changing, and then 1 was subtracted from that. And see if my parentheses match up. It looks like I'm good. So if you notice here, it actually highlights here what we don't know, which is the H that's changing. So what we need to do here is we want to return that dH over dt, the change in height with respect to time. So if we set that equal to the right-hand side of what that is equal to, that will be the negative area of the hole that the fluid is draining from, so negative A hole, divided by AC, the cross-sectional area of the cylinder, and this will be multiplied. Here. Um, what is this multiplied? Negative A hole times AC. It's multiplied by V2. That's right. V2. So that will return us what we want, which is the change in height with respect to time. Okay. So I'm not going to run this, but I'm going to. Okay, so what we want to do next is we want to go ahead and solve our initial value problem. So we'll go solve IVP. And what I need to do here is I need to import the function that will allow us to solve initial value problems. So I'll go from scipy dot integrate. Integrate import solve IVP. And since we will be making a plot of this, I'm going to go ahead and import the tool that will allow us to make subplots. So from plotly.subplots, import make subplots. Okay, so I'm going to run this, run our others here. And actually, one thing I want to point out here is I did make a mistake here that I did catch, luckily. We want to set the height equal to this y vector here, and we want to be grabbing well, it's going to be the only value, but we want to grab the first value in this vector. So that's why we have this bracket of 0 here. So it's the height that we want to set this equal to, because that will give us our height values. So I'm going to run this, and we'll go ahead and solve our initial value problem. Now what we first need to do is supply our function, so right-hand side. Now we need to have a time frame, so go 0 to t end. And again, this now brings in one of my knowns that I brought in. It's not really a known, it's something that we can change within the code here to view our plot. Right now I have it for 10 seconds, so it'll go from 0 to 10 seconds. Now we need to supply our initial height. I'll put that as a list, so hi. Okay. And the method here of integration, we will use Radul method. Oops, if I could spell. I don't know if this needs to be capitalized. Radul. No, it's oh, okay, there it goes. So that's the method, and our dense output here, we will set equal to true so that it runs correctly. So I'm going to go ahead and press Shift Enter, and we can see that it works because in our solution here, it gives us this ODE solution here. So what we can do here is I'm going to set this equal to some variable name. I'm going to call it a res. And if we look at our at what this solution is giving us, if we input a time here, so do res.solution, and what happens here is that if we import a time of 0.4 here, this should be 0.4. I'm gonna go ahead and run this. What it gives us, this array here that it returns, is the height of the fluid at this time of the simulation. So it starts from 0, and if it goes from 0 to 0.4 seconds, this is now the height of the fluid in the container. So we let's go ahead and plot this up and see how it looks. It's not going to be accurate, and I'll explain that in a minute. But we can go ahead and plot this up. So we first want to literally space out some time points on the x-axis. So np dot linspace. I'll start from 0, go to t end, and we will plot 500 points. And then we will do fig equals make subplots. And then we will add a scatter plot. So we'll do fig.add scatter. Our x values will be these t plot points, which is why we made them, so we can plot them. And our y values will be this res.solution, and we want to plot them for all of our t plot values, so that they are in sync together, if you want to think about it like that. And we will want to have a list here of, let's see here. So tplot, we want to have a list here, and we want to be grabbing the first value in this list, because what happens here is this returns an array or an array of 2 values. So what we want to do is grab the first. So I'm put that in brackets there. Now I'm just going to change things like the height and the width, and I'm going to change the color of the plot. So we can do that by doing fig dot update layout. Going to set the width to 600, height equal to 600, and I'm going to set the color of the plot to have a dark background. So if I do let's see here. I'm trying to remember how to do that. Let's see. I'm just going to leave it as white now. Can't remember the command. It's plotly dark. Is the command we have to enter, but I don't remember what that is equal to. So I'm gonna go ahead and just plot it as white. It's not gonna change the values that we get. Update layout and spell update right. Update layout. Okay. So here is our plot. Now, like I said previously, this is not correct, and we can see this is not correct because what should happen is we should start at some height, and we should go, and as time increases, the fluid the fluid level height should level out. It should be going down and then gradually be leveling out because the velocity is constantly decreasing. But what is happening here, and this brings in why I took the absolute value here, is that if we didn't have the absolute value here, this square root that the code is reading, we would get some values that are less than 0. And obviously, we can't have a negative number under square root. So if we didn't have this absolute value here, we would get an error. So in order to actually get this plot, I went ahead and already put in the absolute value here. But what happens here is that we want to stop this this calculation here at 0 because this velocity is not going to go negative. So in a real life scenario, we need to stop this velocity v2 at 0. And what's happening is it's having some round off error. So that's causing it to add up a number, add, and eventually it goes negative. And on our plot here, we see that it would level out, and then the velocity would all of a sudden, it would start going faster and faster again, and the fluid level would drop. That's not actually what would happen. So we have a calculation error here, but there is a way to fix that here in our simulation. So what we need to do here is we need to create something that is called an event here in Python. So essentially what we're going to do, like I said, let me get rid of this comma here. We want to terminate our calculation when the velocity is equal to 0. We don't want it going past that, or like we see, we get a result like this. So when the velocity equals 0, sometime around here, we want to be able to terminate our calculation and thus terminate our plot as well so that we are getting the correct answer. So there's something that we can do here in Python. I'm going to go ahead and add in a block of code. Put it up here. I'm going to go ahead and define an event. So I'm going to call that event v20. So when the velocity squared is 0, call that an event. We'll have t and y again, just like above, and we're going to copy this over. So we have our h values. And what we will be returning from this event, so here we're essentially creating our event. So what we need to create this event for is our v2. Now we don't need the square root or the absolute value because we won't need that because we want to stop it before it gets to the point to where we would need square root or absolute value. So just taking this portion of it to return this, we can create our event. So now we essentially have created our event, and what we want to do is we want to terminate this calculation whenever this event is 0. So how to do that, we do events dot v20, or is it event? I think it's event dot v20 event dot, or it's not even an event here. I think it's just v20. Let me put my parentheses there. Take this out. Event dot terminal equals true. So this will allow us to terminate the event basically when it goes to 0. So now that we have created our event and said that we want to terminate this calculation when this event goes to 0, we now need to update here our initial value problem. So our events, and we will need to supply a list of our events. Well, we just have the one, which is v20 event. Again, the velocity square going to 0. And let me see if I ran this. So the last thing we need to do is we don't want to end at tn now. We now want to end we have still our res here. If we do t underscore events, we want to grab the first array in the list that it supplies, so 0. And in that array, we also want to grab the first value in that array. So we'll do bracket 0 and bracket 0 again. So if we run this, we should now get the plot that we are looking for. So as you can see, this does work. And what this tells us is that sometime around 4 seconds here, I believe, yeah, our units are seconds, the velocity goes to 0. So we could set it up so that our plot continues on with no slope here at this point. But this allows us to see where the velocity does go to 0. So at 4.55, something very close to that is when the velocity will go to 0. Now we also have the height of the fluid here as well. So just a quick recap, we went ahead and inputted in the values that we were given. So the external pressure, the initial fluid level height, the height of the cylinder, the density of the fluid, in this case we're dealing with water, the cross-section area of the cylinder, the area of the hole that it has been punctured where fluid is leaving, and we have successfully been able to plot the change in fluid height, which is decreasing as a function of time as the fluid drains out the punctured hole. So that will do it for part 1 of this homework. Thank you for watching.